We've all been there, driving down an old dirt road, feeling every single bump and pothole rattle right up through the seat. That shaking you feel is the perfect starting point for understanding what engineers call a dynamic disturbance. A vibration is motion swaying around a stable resting position, like a parked car on a flat line. Hitting a bump moves it. Inertia pulls it down, but built-in springiness acts as a restoring force, snapping it back. This creates an ongoing, invisible tug-of-war. Inertia pulls the object one way, and the restoring force pulls it back. This battle happens inside almost every solid object when it gets disturbed, from a tall building caught in the wind to the engine running under your car's hood. Understanding this back-and-forth struggle is the only way engineers can design machines that run smoothly, instead of rattling themselves to pieces over time. When we look at things on a massive scale, we can see why this matters. A brick building looks solid, but during an earthquake, the entire structure starts to act like a spring. If the shaking is strong enough, the internal forces become too much for the materials to handle, leading to a total collapse. We also see these forces during sudden heavy impacts. When a massive airplane touches down on a runway, it's hit by a huge force that lasts only a fraction of a second. This sends temporary ripples of energy through the wings and body that the plane has to be strong enough to absorb. Even small vibrations are dangerous if they never stop. If you bend a paperclip back and forth enough times, the metal gets tired on a microscopic level. Engineers call this fatigue. It's when a part eventually snaps because it was shaken just a few too many times. Even when a machine doesn't break, unwanted motion can ruin its work. In precision manufacturing, a tiny, vibrating chatter at the tip of a cutting tool can leave a rough, uneven finish on a part that was supposed to be perfectly smooth. Whether it's making a passenger feel sick or causing a machine to fail early, vibration is a constant challenge that engineers have to identify and manage every single day. To stop a vibration, we have to know exactly what kind of shaker we're dealing with. Engineers use a few simple categories to sort them out. First, we look at the source. A free vibration is like a struck bell. It's a one-time hit that slowly dies away. A forced vibration is constant, like the steady hum of a running motor that keeps pushing the system every second it's turned on. Next, we look at how the machine reacts when we push harder. In a simple linear system, if you double the force, the shake doubles too. But in non-linear systems, like an overloaded spring being crushed to its limit, the way it moves can become chaotic and much harder to predict. Finally, we look at the pattern. Some shakes are perfectly predictable. It's like a steady drumbeat where you know exactly when the next hit is coming. Others are random, like a car driving over gravel. You can't predict every single tiny bump, but you can measure the general roughness of the whole road. Engineers use these categories as a checklist. They inspect for worn-out parts, listen for specific humming sounds, where vibration is strongest, and measure the object's natural rhythm. Once they have the data, they can change the design, perhaps by adding weight, making a part stiffer, or adding rubber mounts to soak up the extra energy. By putting the vibration into the right category, engineers can use math to find the perfect solution to keep things steady. So far, we've treated all this shaking as a problem. But what happens when we want a system to vibrate? When we control these forces, they become incredibly useful. In food factories, engineers use a steady, predictable shake to gently move and sort through millions of items with a level of speed and care that human hands couldn't match. We also use massive industrial shakers to test parts before they ever leave the factory. By intentionally shaking a new machine in a controlled way, we can prove it's durable enough to handle years of real-world use. Shaking can even be therapeutic. There are special platforms designed to send vibrations traveling through the whole body, which can help with physical recovery and muscle conditioning. When you understand the physics behind it, vibration stops being just noise or a nuisance. It's actually a predictable way to move and use energy. So the next time you hear a car rattle or feel your phone buzz, take a second to think about it. You're feeling that same invisible tug of war between inertia and springiness, working right there in the palm of your hand.